So let's see if it is. Okay, at least this is the version that, yeah, I guess it's close enough. So yeah, so let's continue. Like, so we ended like last time to talk about, okay, some trying to talk about some machine learning, and we ended like to talk about it like on SVM. Basically the major concept of SVM is you can think of that as just a single neuron network. You can say a network is not really a network since you only have a single neuron. So it's like a linear classifier. So you just have two classes and you have a linear boundary, but you're trying to maximize this margin here. So if you have the boundary here, you can define a margin like this. You have like one class of data, another class of data, and then you try to find the boundary such that this margin is as big as possible. And last time we showed that, okay, this margin, the length is just like 2 over W, with W basically is some weight data weight parameters here. And more precisely, we have on this side, we have like Wx, like W dot x, or like maybe I write it as an inner product Wx minus B is bigger than equal to 1. And this on this side is exactly equal to 1. And on this side is a Wx minus B is less than equal to minus 1. And here, like precisely on this side will be like Wx minus B is equal to minus 1. So then we can label like this part of this data, let's say with all label 1s, and this data is all label minus 1. So then like we can summarize like this condition here that we want to make sure all this data is like fall on this side, right? So therefore, like you would like to have like 1 multiplied by this guy here is bigger than, or actually I can put this together like this. Let's say I have any data point here. Let's say have like xi, and I know the label is equal to 1, right? So or like the label is like yi here, yi is equal to 1. Then know that like I should have maybe I use this here like instead. So then I have like w times xi minus b times y minus 1 should be bigger than equal to 0. And on this side is the same as well, because I have like this one, I have for example, like one of these point here have label minus 1 here, or y I is equal to minus 1 here. And I should have like wxi here minus b. Okay, this thing is less than equal to minus 1, right? But then I multiply by yi here. So multiply by minus 1 here, this will become bigger than equal to plus 1, right? So then I move this like on this side. So either way, like you can summarize this constraint into just one equation here. So then we have minimizing. We like we want to maximize this gap, right? As we said, like maximize like 2 over W subject to this constraint here. This is not just constraints, constraints like multiple constraints, right? For each of these points, like data training data points, we should have like this satisfied. So maximizing this is equal to minimizing this, right? So I can just minimize this instead. And by the way, like So this, like, we call this a hard margin SVM like formulation. So it's a little bit ideal because for example, if I have some outlier during training, or like maybe simply your data point are not linearly separable, then I may have say some of these points here, like for can never be separable like by a linear separator. Right? Here, for example, if I have one of these like back points here, like one of these labels, like one here, like following here, then there's no way I can find any separable, linearly separable margin, right? Or like boundary, right? So what we can do is we'll just assume some of them will be outlier. So instead trying to um, force like every points to be like outside this margin here, will allow some points will be inside the margin, but at the same time we want to minimize this violation as much as possible. And the violation can be like for each point, the violation can be equal to CI here. So for example, like I have this point, I will have like CI here will be bigger than one, bigger than zero. And for all of these points here, like CI is zero. So then our optimization problem like can be replaced by like, okay, I will try to minimize the same thing, but added a penalty uh, of some of all the CI and scale by some parameter C here. And then like then the constraint here, you see like the difference will be like now I relax a little bit. I have like this minus CI here, right? Because now I can allow that this doesn't need to be go outside, always outside this margin here, but sometimes I get into the margin. So um, now if we look at this optimization problem, like this, and we call this okay soft margin SVM. By the way, this formulation is soft margin SVM. Um, now if we look at this formulation here, so how do we solve it? Okay, maybe I really suppose like okay, I suppose now just a question like so how do we proceed like so I would say like I need some kind of technique to solve this, a very classic technique. So what you may see that like in some of your classes, maybe like uh physical math, is that called physical math? Like what name of the technique? Or like how do we proceed here? Uh, yes, I'm looking for yeah, Lagrange multiplier. Yes. Um, so we have this constraint like is know that this is a if if I don't have this constraint, let's say like I don't have I have this parameter. Oh, by the way, like we need to um be careful like what are our variables and what are actually given like from the problem. So know that like we are given this x and y here. Basically the training data here, right? We know the location of this x here and also what kind of labels here as the training data. Um, then we we have the variables here, basically the w, right? W and b the bias, and also like the c here are the variables. So if I don't have any constraint with these variables, I can just do a gradient, set the gradient equal to zero. I can take partial derivative with respect to each of these variables here. I'm set it to zero. But since I have the constraint here, I need to first I deal with this constraint. I can convert that into an unconstrained optimization problem. So that is using this Lagrange multiplier. So we'll basically absorb this constraint. So we define a new function here. So as something like absorb like each of these constraint here, let's say for a constraint, let's look at just this one as an example. If the constraint for Ci equal to 0, bigger than equal to 0, let's say I have C0 or C1 bigger than equal to 0 here, right? So I add the constraint is equal to basically C0 minus 0 times R0 as a kind of like a penalty to kind of take care of this constraint. So now you look at that, like if I have this term here, and then if I try to maximize this, you see like originally I try to just minimize this thing, right? So now replacing this thing with like maximizing alpha, um, alpha, actually I'm probably should write more clearly. Both alpha and r is bigger than equal to 0 for L. So something like this part here now is replacing by maximizing L for R bigger than equal to 0 and alpha bigger than equal to 0. And this R and alpha here, oh, by the way, like this is like actually it's a shorthand notation here. This is like a vector. So like it's the entire vector is bigger than equal to 0. So I have R here, like actually is like the entire R1, R2, and so on. And I have like each of these to be bigger than equal to 0. So this is like what this is saying here. So what I'm saying, like, let's say I just look at one penalty here as an example. So if I force like R bigger than equal to 0 and trying to maximize, like, okay, trying to maximize L with respect to that. Now, if I have this constraint, let's say if this constraint is violated. So let's say if I have like C0 is less than 0 here, so this is violated. So what? So let me just clean this out. Just question here. What will be this one? What is this one if C0 is less than 0? So one of these constraints is violated. So what will be that? So you can just look at this equation here. You have one of this term here is basically minus R0 C0, right? Any guess? So is the question clear? Yes, the question is that you see like now we are trying to use Lagrange multiplier to absorb like this constraint. So like we introduce a new L here. You see like L here is just this original objective function plus some penalty terms is like absorb each of these constraints multiplied by this Lagrange multipliers, right? So alpha I, Ri, so on. So for this guy is like Ri, Ci. Actually, I can write like this. Actually, Ci minus 0. And this whole thing we call L here. And if you look at like now, if I try to maximize L with respect to alpha, R is bigger than equal to 0. So, or actually this more precise is alpha 1, alpha 2, and so on, all bigger than equal to 0, and R1, or like start with 0, like R0, R1, and so on, all bigger than equal to 0. Now, the question is like, if I have this this problem here, maximizing L with respect to this alpha and R all bigger than equal to 0. And if I have one of these constraint of violator, for example, if I have like C0 is less than 0 here, so what will be the value of this thing here? So is the question clear? Are you guys thinking or like, yeah? So you can look at, oh, actually, you can think of this literally, like, now if I try to maximize, yeah, you can plug that in, but like it's quite conceptual as well. I mean, like you can put that in, but at the same time you look at that if you understand really the rotation and like what's going on here. Um, it doesn't involve like complicated algebra or something. So just imagine now I have let's say one of these R0, right? Note that the point is that R0 can be anything, big anything, like as long as it's bigger than equal to 0, right? Yeah, okay. I guess I will just erase this question. Okay, I'll just give out the answer here. So I'm not sure, maybe like you guys see Lagrange multiply before, but never really think of like how it actually, why it actually works. So uh, know that like if I, for example, if I have one of these violated, let's say if I have one of these uh, C0 is violated, like C0 is less than 0, then in this sum here, in the L here, or like in this sum here, that's one term like R0 minus C0 here, right? And note that I'm trying to maximize this L here, this entire thing here, with respect to all these alpha 0, and so all these alphas and all these R's here, and also like this supposed to be bigger than 0. Now, if like I have like one of this C here is like less than 0, so let's say I have C0 is less than 0. Now, what's the maximum value for that one? Just look at this term here. So this guy is negative, right? This is negative, this is negative. So this together is positive, right? So and positive and bigger than 0 as well. So since our 0 can be anything as long as it's bigger than equal to 0, so just this term itself will be infinity, right? So this term is already infinite. So therefore, the L itself, like the entire L here, will be infinite. So you see, like if I added these penalty terms here, so any of these constraints are violated, then like this will be infinity basically. Now let me just erase everything now. So with this penalty here, actually, this part here, as long as the constraint is not satisfied, this will be infinity. So if it is satisfied, then it will be something finite. So because you have the outside loop here, or like what's outside is you're trying to minimize things, right? So therefore, anything is infinite is not going to be picked up. So therefore, like this will always give you a solution that like will satisfy the constraint. So basically, everything like violate the constraint is infinite. So therefore, we'll pick the one that doesn't violate the constraint. That will be finite. So therefore, like that's why like this is actually an equivalential formulation here. So okay, I just try to kind of explain like if in some of you guys may have seen like Lagrange multiplier before, but maybe you don't know why it actually works. So now, so instead, like therefore, like we consider this problem instead. And typically the trick here is like we can swap this like two optimization problem here. Instead of doing a minimization, then maximization, we can do maximization first and then minimization. But if I do minimization first, you see, like this is an unconstrained problem, right? So with respect to these variables are unconstrained. So now I can just take the gradient and set it to 0. So I take partial derivative with respect to W, with respect to B, and so on. I take it to 0. So with some algebra, you can do it yourself. You will get something like this here. And actually what's interesting here is that like if you look at like now what's leaving behind, it's just that I'm trying to maximize over alpha here. So apparently because you solve the partial derivative with respect to this guy equal to 0, right? So all these dummy variable will be gone. So I have alpha and R, and we find that R is related to alpha. Actually, R even somehow like why is that R? So anyway, like yeah, so alpha will be the only variable left behind. And for this one here, also like given the alpha, now yeah, W, what's interesting is the W, right? W is will be given by this one. And look at this equation also, like for this equation, why SVM is so attractive in the past is that this is actually a very easy problem to solve, because if you look at this here, it looks complicated, but remember like these are just constant given by the problem here, right? This is just constant here. And what you have is just alpha I here and alpha I alpha j here. This is just a quadratic equation, right? So it's a quadratic equation, like second order, right? So, and you know that like for quadratic equation, like what we can do, okay, first thing is that what we can do is that I have like this alpha 1 or like alpha stuff and alpha 0 and so on, maybe up to alpha n. And I have like this quadratic equation here with respect to these alphas here. So what I can do is I simply, each time I just take all this alpha to be constant, like I fix all the alphas and just allow one alpha to vary. So then this is precisely a quadratic problem, right? So for this quadratic problem, like we will have closed form solution for that one. So we know that like, okay, for quadratic problem, like that's always have this shape here. And if we want to maximize that, okay, we want to maximize that. So therefore it should have this shape here. So we know precisely the maximum say in closed form. So we can just iteratively like fix one variable, or sorry, fix all variables m except one, and then move along that and then keep iterating and get the solution. So so once we find the alpha, then again like W will be just given by that. So therefore it looks complicated, but actually it's simple. It's easy to solve like computational wise. And that's why like if you you use SVM nowadays, like you can use for example like scikit-learn this scikit library in Python, and there's a SVM fit and so on. Like you yeah, typically like you can solve a pretty large problem like very quickly. Like you train a problem like in minutes. So, but on the other hand, if you have a deep learning problem, multi-layer neural networks, yeah, you can take weeks to train that like for large model. So and by the way, just to mention that like this is the original SVM is formulated as like a binary classification problem. We only have two classes here. So and we mentioned like last time that uh, in machine learning, or like more precisely for supervised learning, uh, you are essentially fitting model, right? So you have like given some inputs like X here, you're trying to fit output like Y here for the Y. So you want to find this function like fx y equal to fx here. So find this function, and this function will be probably parameterized somehow, like, or like this is maybe inherently parameterized, maybe like uh, based on like your model. Like, so in this case, like for example, this theta here will be this W and B here. Um, and if in our case here, the label if discrete, then like it's a classification problem. Like in this case, only have two classes. So if I have a continuous labels here, so it would be a regression problem. So we can use like SVM, like similar idea. Uh, actually, I show a similar idea of SVM for do regression. So again, like it will be a linear regression thing, but like we can use this margin concept again. Like in this case, we have this support vector regression is like trying to have the points like not go beyond the margin. Now we fix a margin here, uh, and we want, or like we define this margin here as a the maximum distance of the data points like from the boundary or like for the estimation from the estimation, and then we try to more or less like minimize this margin here. So and we will have a hard margin. I will just quickly like go through that without going into detail. So you have a very, you see like very similar formulation here. So we have, instead of like trying to, yeah, it's more or less the same thing. Like we have minimized that, but the constraint you see here, uh, instead of like trying, like instead of like constraint something like this one here, so we have this has to be outside this one, right? So this label multiplied by this guy here has to be bigger than equal to 1. So we'll have like this, basically this estimate from your ground truth will be less than this margin here, this epsilon here. And we can have some soft margin formulation as well. So we have like this added, like I guess again like some dummy variable ci here that we can violate the um, basically this margin a bit. So like it's, I can, some of this point can go outside this margin here. Then in this case, like the ci here will be like bigger than 0. So okay, I guess I'll just flip through that quickly. So then again, like the point is like if you go through the same thing, same math here, you will uh, using Lagrange multiplier, you will end up like trying to solve for some alpha again. And I again, like it's like a different equation, but the key point here is like it's still a quadratic equation in terms of alphas, so therefore can be very easily solved. So once you get the alphas, like you can find the W again, like with forms like this. So another remark here, like why SVM and SVR are so popular, is that like it usually combined with so-called kernel trick, because like in reality, like it's many situations that like you cannot separate your data points in using just a linear classifier, right, to have a linear boundary. Just take a case here, like for example, I'm in one dimensional case. I have data points I here is one class. I have this as another class. Apparently, I cannot have a linear classifier because I in 1D, a linear classifier would be simply I have one separator here. I'm saying like points in here, I mean, points are smaller than this threshold will be like all belong to one class, and points like above this threshold will be all bigger than one class. Of course, I can introduce a soft uh, this soft margin formulation. Then these are all outliers, but this will not be a very nice kind of like nicely separable like case like using linear classifier. So instead, like what we can do is like we can project this data point into high dimensional space. So for example, if I have data point like this, if I project to 2 dimensions, so now if I into a two-dimensional case, so I can have like these points here actually is here, and this rest of the points is like here. So then I can separate that in the high dimensional space. So in practice, like it can be done like that very easily using this so-called kernel tricks. Note that like in the support vector machine and the support vector regression, for both formulations, like for the involvement of the using the data point like x here, it's just like require the inner product of x rather than like you need to kind of like use the x directly. So, and this is like for support vector regression and also for support vector machine as well. You see that like it always only depend on the inner product of x rather than like x itself. So therefore, like okay, even though like if we project to high dimension, basically like we know that we can project to high dimension and then like we can always separate the data. But I don't know like how far we should project. Like it ideally actually we can even project to infinite dimensional space, then like we can always like separate any data points or any any distribution of data points. So and of course if we project to infinite dimensional space, we don't know how to compute this inner product directly, right? Because then this will be infinite length vector, this will be infinite length vector, and do the inner product itself will be like it need infinite amount of computation. So but we can use this kernel trick is like we don't actually project into the high dimensional space because we just need the inner product, right? Instead, like we just have a kernel function like to replace these operations. That means that like I in reality, okay, let me start from here. Let's say I have x1 and x2 here. Since I only need to know the inner product x1 and x2, right? So if I have this project to high dimensional space, I should have x1 mapped to some x1, x2 matched to some high dimensional space. Like find x1 and find x2 here, and then find the inner product like find x1, find x2. So these factors here can have like infinite dimension, like n by 1 and n can goes to infinite. But instead of going to a step like this, like one step at a time, we'll just like go directly from here to here and using some kind of a kernel to just say like for this inner product of like 3x1 and 3x2, we'll just say, okay, this will be equal to k x1, x2, and k will be some kernel function. And you can solve theoretically that like if I have something like the Gaussian kernel, that like k x1 x2 is equal to like exponential x1 minus x2 square sigma, something like this thing here, then let's see, yeah, something like this here, then it's essentially project to the infinite dimensional space. Yeah. So okay, I have a whirlwind tour introduction, I guess, of SVM and SVR. So I guess I would just leave it there and go back to talk about like neural networks. Now we look into cases that actually have more than one neuron, and so remember that like, our original motivation, like using machine learning, is that like for many of these problems, like for example classification, we just don't know how to do it like using classic algorithmic approach, right? We don't know how to write an algorithm to do classification of like an image into an app, like classify image, whether it's an apple or like tomato and so on and so forth. And now we have this data-driven approach. Again, it's like classically, you can think of like this is like P neural lateral, not P neural lateral, P deep learning era. What people like in machine learning or in computation typically do for this kind of problem. For example, if I try to do a image classification, first I try to extract some image features. Like for example, like we have these SIF features, right? Or like we can extract edge features, or we can just like using PCA, like principal component analysis, to do a dimension reduction of this data. And anyway, this will be like some kind of, if you don't know PCA, it doesn't matter. So it's just another way to, you can think about another way to extract features. And once we extract the features now, so, and we will just train a classifier here. So this can be like, for example, SVM here, and then like given the label, then we can train this classifier, train the SVM, and then I have a learn SVM model. Right? So now when I test it, when I use it, then I have a new image. I go through the same process to create the features, and then like pass to the SVM model. Then the SVM will tell me like whether it's a cat or a dog and so on. So this is like the P deep learning approach. Now the in the past, like what people did is like we will always try to like hand engineer these kind of features. I decide like what features are good, what features are bad. So eventually people find that okay, if I use like a deep neural networks, like with multiple layers, we can get away this procedure, like thinking like if I have like multiple neural networks, so we can, oh, I don't have a, it's okay. So let's say I have multiple layer neural networks, right? So I have like earlier layer, later layer, and so on and so forth. So you can think of like the earlier layers actually doing the job of like extracting features, and the later layer is like trying to do the classification. So and the model, like in this sense, like you can train it like so-called end-to-end. So you're simply giving the input image and then giving the labels. Now you train the entire classifier without you engineer the features. Like you don't decide like what features are good. You don't decide like whether it's edge feature is better or SIF feature is better and so on. But you just plug this thing like directly into the model and train it. So actually, it's even easier. You say like in terms of an engineer job, like I don't know, like what I don't know what engineer is supposed to do in the future. Like you just put everything to the computer and let it to one basically. So and then like uh ideally like you just like babysit with this model, like maybe train like for like a couple weeks, depends on how fast on your computer and how big is your model. Then you get like something okay, a model that you need to evaluate whether you did a good job like in training, did you mess up something. Yeah, this is more or less like you're going to do with this machine learning approach nowadays. um and so okay now we give a high level like what's supposed doing like for this neural approach nowadays, right? So now let's go back like how do we actually train that. So again, I focus on just the supervised learning problem here. We always have, say, given the input data, and also we know the exactly the label y, so we know the ground truth there, and we're trying to like find the optimum w. W will be like you can think of this extra just as kind of like summarizing like all the parameters that you use in the model. Um, and So, okay, do I need this? Yeah. So, if if you look at that, okay, so precisely again, like what we're trying to do, doing indeed, like if we have like this kind of model, again, it's nothing but just a and solving another optimization problem, right? So our objective is like we given some labels, let's say y here is the ground truth labels, or like the training there's basically a label like given the during the training. Um, and we are given the data point like also during the training. Now I want to find the best model or like best model parameter such that like this matches one another, or this get as close as possible. So I can in general define some loss function here, or like typically we can just make this loss function is just a this a square difference as a L2 norm. Um, and I'm also like I can add some this kind of like so-called regularization penalty here. Just like this will be, for example, like I can add this as like the norm of the W here. In the sense I want to reduce the complexity of W sometimes. So we don't want to make the W too complicated um, for various purposes. So now this become like, okay, I have like this objective function here. Of course I should sum over all the data points, right? So I should sum over all data points here. So if I have n data points, I should just add all this together, right? And I should just try to now minimize this with respect to W here. So again, it's just a optimization problem here trying to solve. It's like what's going on for SVM. But the problem is the difference is like SVM, we have the problem, know that like it's a simple quadratic problem there. Uh, and but here, because I have this F here, this model here in general is like nonlinear. So I don't have a simple quadratic function, quadratic problem with respect to W. So therefore, this is a much more challenging optimization problem. Like for example, if you remember, if we have the actual neural laterals is uh we have a new ones, it's like just weighted sum, like artificial new ones, it's just weighted sum of input, sum together, and okay, weighted sum by W, right? This is some weights here. And then I go for an activation function here. And this activation function is that actually that lead to this nonlinearity in F here. So and just one new one, you have some nonlinearity, and you have like multiple layers. Of course, you have like the entire model is very nonlinear. Um, so um, to solve that, before solving that, let's look at one more example here. Actually, um, so let's say go back, like we have this formulation, but we go back to a simple linear regression problem. So that's basically we are trying to fit the label Y with a linear model, let's say W here. It's like the support vector regression, but um, is we don't have we don't use the uh, loss function I define as like in SVR. We I mean the objective function there is we're trying to minimize the margin, something like that, right? So here like we I'm also subject to the constraint that we have the margin always we have the data point always like if for some support vector regression we have the data point always like inside the margin, but here like we simply let's say trying to minimize a loss here. So we want to minimize the difference of our estimate from the ground truth there. And we can have like a regularizer, let's say we just say, let's say minimizing uh, the sum of the coefficient of the weights here. So that will be the matrix law. If you don't know that, this is like for matrix here, this so-called like for Venus law is basically just like if I have a Wij or like if I have matrix here, W matrix here is like W11 or like WM1, like this is like Wij, let's say, or maybe I just write this WNM, let's say. The Frobenius norm is just sum square of all these elements of that. Um, Now, as we just mentioned, the learning problem is just this way. We try to minimize this thing here is our learning problem. In this case, a linear regression, then it's probably solvable like analytically. That probably have a closed form solution here. Uh, now, uh, maybe again, maybe it's a good place to pause. I asked this question in the past also, like in another class. So I'm not sure you guys, like if you are in the other class as well, if you remember that. So now if I want to uh, kind of like increase the complexity of our model, so earlier we just have a linear model like this, where you have like one W here, and my model is I just have the input X multiplied by this weight W here will give me the output Y here. Um, Now, if I introduce a new model, I want to introduce new complexity here, I may multiply an additional W here, right? So does this make sense? Like, do I get a more kind of like richer model? Like this question here, richer model than before compared with this guy? Like if I, instead of like just one W here, I I I multiply by another W, do I get a thank you for the answer. So at least I know you are still around. So yes. So so anyone else? Yes. So yeah, many are followers. Okay, some have to make up their mind themselves. So yeah, answer is like no in this case, because if you look at that, like I can just consider this W2, W1 as a one matrix W, right? So therefore you don't actually get a virtual model just doing that. So I can put up W1 and W2, but then you can think of this as just one W, right? So then I can have this model like totally capture this one as well. So if I have W1 then multiply W2, then I just call this W2 times W1 as W, then we'll just go back to the original formulation. So, but how can we get it richer? So basically, like we get it richer by like introducing some nonlinearity in the middle. So I can like after multiply W1, then I can like do a kind of like nonlinear things here. So for each of the element, so by the way, this should be a vector. It's because X is a vector, W multiplied by X is a vector. So this is a element-wise a operation. So for each of them, I can have like some yeah, it's written here. And element-wise a nonlinear function. So for example, it can be a sigmoid or step function or like anything. So then now this will be a richer model than this one here. And this is essentially neural networks, right? So it's like this is a, you can think of this as a first layer, then I have activation function, and then second layer, and so on. Um, and uh, and we can like again like make many layers. So this is a kind of repeating what we talked about before, but in a more uh elegant way, like in a matrix form. You see, like we can like when we kind of like organize these neural networks into layers, then for individual layers can be just like represented using a matrix multiplication followed by activation function, matrix multiplication, activation function, and so on. So for example, if I have a model like this with one hidden layer, it's really like I have X here as a vector multiplied by W1, and I get for a activation function here this nonlinearity, maybe I can use a value, something like value is popular. So I use a value. And then like, I guess, hopefully you guys still remember what's value. Value is like, just I have like, if the value is like bigger than zero, then it will be just equal to the input. If the input is, sorry, the output will be just equal to input when the input is bigger than equal to zero. Otherwise, it will be equal to zero. So yeah, after the activation function, I can multiply by another W2. So it will be like this. So then the output is just, this thing is just representing this figure here. And I can have like 3-layer levels, like again, like can be represented very concisely with this, with this matrix formulation here. Now, so go back to the question, like how do we solve this optimization problem here? So now with this formulation, you see that like I'm basically have like these layers of network with ways here. And my objective here is I find this W, right? Okay, always don't forget your objective here. So the objective of supervised learning is you have this given this training data point here, and you have to given the labels, output labels here, the corresponding output labels here. I want to make sure that these are close to this one. So I can basically define some loss function like this should be close to zero. So or like, therefore I try to minimize that. And with respect to like W1, W2, and W3, and so on. Now to find the best way, so again, I will be have something like this, right? So I'm trying to minimize this thing, like just consider this like just rewrite this is a simple function like G function of W. We're just trying to find the minimum way. So there's a lots of ways to do that. Actually, not lots of ways, but lots of potential ways to do that. If for some problem, like actually it's typically just toy problems, for example, like for linear regression, and I cannot say SVM is a closed form solution, but like it's linear closed form solution. You can solve that like partially closed form because it's a problem is closed form. But for many problems, like, for example, for neural networks in general, it does not have a closed form solution. You cannot really try to minimize that using like simply, okay, take the gradient and see like what happened. Very silly way to do that would be maybe I take some random W. That's actually it's a silly way, but if you think of like evolutional computing, like sometimes it's like doing something like that. So genetic algorithm, like yeah, partially is like that. So even though yeah, it's pseudo random. So I don't it's uh yeah, I shouldn't say more. So I may probably like what is that word, like offend like many people, like as if I continue. So anyway, um so a logical way will be just trying to do I cannot get close form, but I can probably find a gradient. So I probably like at some point like somewhere, if you think of you just like you are in the wild and you want to go downhill, like maybe like you want to go to the lake here, like it's like downhill there. So what you can do is like you don't know what the exact path, but maybe like you can always go downhill, right? Eventually you will reach there. Uh, so and since I know the gradient, like typically that will be able to find that. Like for example, if I have a current point somewhere, probably I can find the gradient. The gradient will point me. Maybe I say like I have a point here. The gradient basically point me like the direction like to go uphill, right? So if I just go to the opposite direction, I will go downhill. So so that's basically the idea in general. People what we will do. So I will just try to find the gradient. So like with respect to the W, And that essentially just meaning that like, I'm trying to find the partial derivative with each of the weights of W. And then I will just go along the direction that the opposite direction of that thing here. And then that will give us the solution eventually. And of course, I cannot just go downhill like all the way, right? Because maybe I have, okay, I don't have a very, for example, if I have a figure here, so the optimum, okay, actually maybe the optimum is here. Maybe I am somewhere here, like here, right? So if I go, okay, maybe it's a good question to ask, like, let's say this is the minimum here. The minimum is here. So what do you think the gradient should be pointing? Like this is a option A here. This is option B here. This is option C here. What's the gradient? So no, the gradient is the vector, is a vector, right? So of course I have like both like, okay, good, yes. Yes, this is going, yeah, the gradient is going uphill, right? So I should go downhill here. So I go downhill here. Note that if I go downhill too far, I don't know, I will be very bad. I will go to just this one here. So I want to go like small step at a time, like small step at a time. Eventually, we probably reach here. So let's see if I think I have the animation here. Oops, why yeah, I have animation here. For example, like if I have point here, this is using like different a small difference of update rules. So you can go downhill like just yeah, I won't go into detail like this one here, but like it's different update rules. Like for example, whether you want to include some momentum or like you want to like yeah, that's basically lots of different tricks for that. So if you're interested, you may take my other class in the future. So we will talk more detail about this. But all these approaches is like based on like going deepest design essentially. But then the question now is like, okay, I use deepest design, but I need to find the gradient here, right? So how am I going to find the gradient? So we will use this known as a backpropagation algorithm, or like it's actually, or essentially it's really a train rule in calculus. It's not really something really mysterious. So for example, like if I let's see what's a good so look at the problems we have earlier. So let's say we have a three-layer neural networks can be modeled with this kind of W here, and this sigma again the activation function of the inputs. And so this is the output estimate. I want to get close to this Y here. And let's say I don't have any regularizer, so I have the objective function is just equal to this guy here. Now I should try to minimize this G here, right? So now I should just go downhill as I mentioned. I should find the gradient with respect to all this. I'm trying to um, kind of have W1 will be equal to W1 minus gradient W1G, and this maybe with some epsilon. So this is this step size here. Sometimes we will call it learning weight here. So and I'm also like so on, like W2 will be equal to W2 minus epsilon gradient W2G, something like that. But then we need to find this gradient, right? So if you have a simple model like this, okay, you may just find it in closed form. I can take the partial derivative with respect to, oh, actually, this you can do some vector calculus to find like W1, W2, this gradient with respect to W1, W2, and W3. But if you have many layers, it will become very complicated and very difficult to do. Um, so, but because like we have the networks ultimately, it's just a network of nodes. So we can do this kind of backpropagation approach, I guess. Let me just look for one example that is like, okay, this is, or maybe, okay, maybe I just have one example. Maybe I look at this one here. So uh, what I mean is that like, given some function here, let's say I have a very simple function here. Let's say if I need to find the gradient, meaning that like for give of this each of these variables here, I consider all of these are variables. I need to find partial derivative of f, the output with respect to each of the variables, right? Each of like x and y and c and so on. So what we can do is like know that, like for example, if I have if I have, let's say I have this I call q here, this intermediate value q here. I have like q is equal to x plus y, and then f is equal to q times z here. So from chain rule, for example, if I need to find partial f partial x here, will be equal to partial f partial q and partial q partial x, right? So I can find let's say I if and basically partial q partial x is what, like, it's the uh, local gradient of some computational load. I call this a computational load, local gradient of computational load of the output given like some input here, right? So and what is this partial f partial q here? Is essentially some gradient that pass back earlier. So for example, like I can get this uh, assuming that I know partial f partial q here, then given that multiplied by the local gradient, I know this partial f partial x, right? Now I know partial f partial x if I have like more nodes like that going backward, then I can like again, if I know the local gradient of this guy, maybe I have like uh, W U V here. So maybe I call this and I need to find like partial F partial W here. And I know this like partial F partial X here. Then this partial F partial W will be like partial F partial X and then partial X partial W, right? So I have this partial F partial X is like just passing backward, like from later layer and multiply by this local gradient here. So then okay, if I go for this very kind of simplified example here, the procedure will be like this. So you have like, let's say the input, like if I have some inputs like 2 x is like -2 5 and -4 here, x y z -2 5 and -4. Now when I go forward, like of course I go for each of these computational node here. Like it's very simple now. It's plus star, plus plus and multiplication here. But I can have more complicated, like any kind of like manipulation. Maybe I can have sine, cosine, or like trigonometry, or I can have like very complicated like uh formulas here. But uh, assuming that like I know how to find the gradient or like partial derivative like for this particular computation here. So now with this input, like in this case, back to this example here, after output here is just like y plus x, right? So therefore 3 here. At the same time, we try to find the local gradient for all of this point here. Okay, maybe like this is a good pause here, like maybe a question here. What is, I call this q here, right? What's partial q, partial x here for this example here? Yes. Yeah, that's very simple, right? Q is equal to x plus y, so the partial group power x is just equal to 1. Yeah. So in this case, like you will basically compute like, okay, the partial derivative of this output with respect to each of the inputs is basically 1 and 1 here, right? And then like also like for this guy, okay, after I compute this output here, now I can work on this node here. I have input side for all the inputs side for this node here. So I have like 3 multiplied by -4, so I have -12 here. Again, I'm trying to find the partial derivative with respect to each of these point here. Okay, maybe like another question here. What's partial? So this is like output is called F, right? Partial, what's partial F, partial Q here in this case? Yes. So I have F is equal to Q times C, right? So I have partial F, partial Q is just equal to C. So therefore it's just equal to -4 here. So so okay, I get the partial derivative here. Like, okay, this for this path I have is equal to -4, and for this path is actually equal to 3. Now going back the gradient, so I have a gradient. Going back here, I have like first like partial f is just equal to 1. I can think of like, okay, this pass back a gradient of 1 here. Now the gradient of like partial f partial q therefore will be equal to partial f multiplied partial f partial q here. It's a little bit silly, but this will be like 1 multiplied by this guy here, right? So it will be equal to -4. So I have a gradient of -4 like passing back here. And then like this one, I have a gradient like 3 pass back here. Then like now to pass back like this to this one here would be like this one multiplied by this guy, right? So I eventually get this -4 and this -4, something like that. So yeah, it's more or less like this. Yeah, as I mentioned. Yeah, um so it's nothing but chain rule. So this is just summarize what's going on. You have this coming in when I have a computational node. First, when you have all the inputs, then you compute the outputs, right? And at the same time, like compute the local gradient. And when I'm doing the backward pass of the backpropagation, when you have the gradient like coming back, then you have like this multiplied by the local gradient and continue to pass back. Note that like I caveat here is like 1D, I show a 1D example here, like in the sense like what I mean is 1D is like the inputs here like and outputs here are all scalar. So when you have like input outputs are vector or like even matrices, you need to be careful. Like for example, if you have a vector like x here and a vector y here and a output vector z here, then the local gradient here, for example, partial c, partial x here, is actually 2 dimensions. So actually the dimensions of this local gradient, the dimension of this one is equal to the product of dimension of c multiplied by dimension of x, something like that. But I won't go into that. Like, so again, like if you're into this kind of stuff, like and if you're a graduate student, you can take my class in the future. So, but this is like the high level idea what backpropagation is doing. And yeah, forward pass. And this is just another example. Okay, what I'm doing time. Like so. Okay. Uh, so okay, like this is a just illustrate like how simple like a neural network can be. This is an example of like a 2-layer neural networks. So you see like you have one hidden layer H here. The hidden layer's dimension is like 64. So you have the input dimension is like 8. Let's see. output dimension, I think, is a 30 HMD. Oh, okay. Output dimension is yeah, okay. Output dimension is 8 as well. It looks like. And I have like 32 data points here. Training data points at 32. So what we're trying to do is like trying to have a very simple little lattice is like this. So I have let's see, H is like 64. So I have like 64 hidden layers. Okay, 64 hidden units here. So maybe I draw it with circles. So I have 64 of them. I have one input here. Uh, uh, oh, actually, it has 8 inputs here, right? I guess. And 8 inputs out 8 outputs, I guess. So sine. Yeah. So okay, like I guess it's time. I don't want to go into. So but it's just very okay. It's also simple because it doesn't you it's basically solve the closed form here. In this case, you find the gradient precisely. This is the gradient here is solve it like cut precisely like closed form, like basically by hand. You first solve it and then find the gradient equal to that and just type that in. And if you use using packages, oftentimes you just need to define the forward pass, define how the lateral is structured. So what computation you are doing, and at the same time, like what are the activation function and so on. For example, if you're using like TensorFlow, Keras, PyTorch, and so on, they will do like automatic gradient computation for you. And then here, like it do an update, like you see, like it's just trying to go down the hill, right? Again, when you find the gradient here, it's just going steepest descent. So okay, I guess I'm time already, so I guess I will stop here. So next class will be the last class, I believe. So we won't have class for that week. So and we'll talk a little bit about CNN, and then yes, but let's see. So if I will stop now, and unless you guys have any questions, any questions, either like questions here or questions related to homework and so on. Like just but uh, if not, I will just see you guys like first day. So
Sam,
yes,
so homework 4 due
yes.
date is May 1st. So we can submit after 1 or 2 days with penalty, or that is the final deadline.
You can have a little bit. Yes, the final deadline. I think I put it a week after that. So yeah, you can like be a little bit late. For the and for the final exam, I mean the final report, like you don't want to be late that much. I guess I forgot like where I put the hard deadline there, but like it will be like a couple of days after that because there's like a time constraint to submit the grade basically. So I believe like I need to, but for all these other assignment, I need to get it before 9. I think like that's the day I set it. So otherwise, the TN and I like won't have enough time to grade all the assignments. If anyone's I still want to submit the late assignments like by that time, yeah.
Okay.
So the homework is due after a little bit later than May 1st.
No. You will have like penalty for that. But if you
Oh, okay.
make it like Yeah, you can, but that will be hard deadline like online. So
Okay.
after like we won't accept any homework. Yeah.
Okay, perfect. Thank you.
Yeah.
So, are we going to have like a discussion over what will be on the final and what we should expect to see?
Oh no, there's no final. Okay, like that's
Oh,
no,
there isn't? Okay, it
there's
shows
no
that
final,
there's a
yeah.
final. Okay.
Okay.
Not so I didn't look in your
no.
syllabus.
Oh yes. No,
I
that's
looked
no,
on one, so
yeah, okay. The final report is like the final basically. The portion
okay.
final. So you guys just work and I put up the a rubric like on Canvas also like for the final report. Like it's common sense basically like what you originally kind of suggest to do and like what you eventually do and like and also like how do you evaluate what you did, like for example like if you say you create this kind of whatever model or like whatever like system and you want to test that like you okay basically want to test them show that show the result basically.
Okay, perfect. Thank you.
Okay.
Also, Dr. Sam, so are there any marks for the video and presentation like we used to have before in the previous courses, like bonus marks?
Presentations I think I
So for the final report, before we used to have some bonus marks if we submit a presentation, make a presentation and submit the report, and submit the video.
yeah, yes. Yeah, for extra credit, like for yeah, yes, I guess we can do that. So I didn't put that in. Yeah, I can put in some extra credit if like you guys yeah, definitely. Let me put that in also. Yeah.
Okay, thank you.
Yeah.
Yeah, do we still have points for participation, since I haven't seen any on the?
Oh yeah, we have because we are a little bit behind that. Like
Okay.
later than yes.
Thank you.
Yes. So okay. So if no other questions, I will just see you guys like first day then.
Thank you. Have a great day.
You too.